Okay, so here's a final example of a relation defined on this set ABC, and so I've just listed the elements of the relation. And so what I've also done is reminded us of here is the definition of what it meant for a relation to be symmetric, and definition of what it meant for a relation to be antisymmetric. So what I'm going to do is draw out the digraph and the matrix. But before I do that, let's think about, does this relation qualify as symmetric or antisymmetric? So for symmetric, if we have xy, then we also have to be able to find yx. Well, we don't have to look too far to see that that's going to be an issue, because if I go to the element AB, if this is symmetric, then I also have to find BA, but I don't see that. There's BC and BB, AA, but I don't find BA. So that's a case that makes the definition of symmetric false. So this relation is not symmetric. Now, so one thing we kind of thought was, well, that probably means that it's antisymmetric, but let's see, is this relation antisymmetric? Okay, so if xy and yx are in the relation, well, that doesn't apply to this element, because we'd have to have AB and BA in the relation. It doesn't apply to this element because we'd have to have CA and AC in the relation in order for this to be able to qualify as true. Of course it's going to apply here, because if we have AA and AA in the relation, then we know that A is equal to A, and same thing here and same thing here. But what about these two? What about these two? Right, so here's a case where we do see xy, or in other words BC, and yx, or CB, in the relation, but it certainly isn't the case that B is not the same as C. So these two guys cause this relation to be not antisymmetric. Right? This is not antisymmetric, and that kind of makes some sense. I mean, these two elements are symmetric to one another, so we can't claim that the relation is completely antisymmetric, right? Because these two are we have BC, and then the elements reversed. Those have symmetry. And we also can't say that the relation is completely symmetric, because if it was, we'd have the reverse of this one, BA, and the reverse of this one, AC. Right? So at the same time, we've got a relation that is not symmetric and not antisymmetric. So there's another case where, kind of funny, we can't immediately conclude that we have one because of the other. Kind of odd. But let's look at the digraph. So we only have A, B, and C in this case, three elements in our set X. And of course we're going to have a loop, because we've got AA, BB, CC, so a loop at every vertex. So that's a quick check that the relation is reflexive. We'd have a directed edge going from A to B, a directed edge going from C to A, and we've got directed edges going from B to C and C to B. Right, so here we've got BC and CB. That fits the definition of symmetric, but we're missing, right, we need an edge going both ways here and also here. in order for this to be completely symmetric, right? So the fact, right, at the same time, the fact that we don't have edges going both ways here and also here, that would lead us to believe that this looks anti-symmetric, but it's not completely anti-symmetric because we do have, between B and C, we do have edges going both ways, directed edges, right? So maybe at a glance there we can tell this is both not symmetric and not anti-symmetric. Okay, and if we were to draw the or write out the matrix, look something like this. So let's see, we've got A related to A, B to B, C to C, so the main diagonal is all ones, it's reflexive. And then what else? A related to B, A is not related to C, B is not related to A, B is related to C, C is not related to B, or I'm sorry, C is not related to A, but C is related to B. Right, so here's the problem. Across that main diagonal, right, that's going to make our relation not symmetric. That's, wait a minute, did I miss one? I did miss one, I'm sorry. I forgot this one. C is related to A, so I did make a mistake in my matrix. C is related to A, so this should be a 1 right there. Right, so this indicates the relation is not symmetric. Also right here, so if this was a 1 and this was a 1, then we would have symmetry completely around that main diagonal. Right? But we do have some semblance of symmetry because right here these guys match across that main diagonal, and that's why we can't say that the relation is completely anti-symmetric, because there is some sense of symmetry there, if that makes any sense. So I don't know that using the digraph or the matrix is necessarily a great way to determine anything about symmetry or anti-symmetry. I would probably stick with knowing how to use the definitions, which is why I kind of reviewed it here, because it might get a little bit confusing. But if you can stick with the definitions, then you can for sure verify if your relation is symmetric or anti-symmetric. And I would definitely stick with the definition of transitive. Of course, using the digraph or the matrix to determine whether a relation is reflexive is relatively simple. But all we were really interested in is just giving you an introduction to how to make a digraph and how to make the matrix for the relation. And we will very shortly dive a lot deeper into graphs of all sorts. So this is a good introduction to that topic as well.